Okay, so the relationship between work and energy. Now, sometimes when we do work, we make things move. And so let's just do a little derivation with that. Work, of course, is a force times a displacement, but we know force is ma from Newton's second law, so we can write that as mad. Now, I can put a factor of 1/2 in front of that, provided I put a factor of 2 in later on. Because the 1/2 and the 2 would clearly cancel out and get us back to where we were there. But now 2AD, twice the acceleration times the displacement, is the same as VF squared minus VI squared. So the work is 1/2 mVF squared minus 1/2 mVI squared. And clearly, this then is an expression for the kinetic energy, because the work that we did made this thing go. What we get as a result of the work is 1/2 mv squared. That's our equation to find the kinetic energy of an object. Now let's do another derivation to see how we're going to determine the amount of potential or height energy. So let's imagine we lift this thing up, and we're going to give it some potential energy. All right, so work is again a force times the displacement. Now, if we're lifting this thing at constant speed, then the force that we're applying will be the same as the weight of the object, mg. And for our displacement, let's use the variable h to indicate the height that the object gains. So we end up with an expression for the work done in lifting this object as mgh. This then is our definition of potential energy of an object. Potential energy, just like kinetic energy, has units of joules. M is the mass of the object, g is the gravitational field, and h is the height. Now, let's just get that back. Okay, so sometimes when we do work, we give an object kinetic energy. Sometimes when we do work, we lift it and give it potential energy. In general, you give it both. And even more generally, the object may have had some kinetic and potential energy at the beginning. Then you do work, you're going to end up with a different amount of kinetic and potential energy. Now, we're going to define E to mean the mechanical energy, which is the sum of the kinetic and potential energy. So if you've got a certain amount of mechanical energy at the beginning, and you do work, that's going to give you a different amount of mechanical energy at the end. So E stands for the total mechanical energy, and it's the sum of the kinetic and potential energy. So this result is known as the work energy theorem. Now, let's practice writing some energy equations. In each case, we're going to make a work energy statement here. So energy at the beginning plus work equals mechanical energy at the end. So let's imagine that we throw a ball, okay? So at the beginning, is there any mechanical energy? Well, mechanical again means kinetic and potential. It's at rest, so there's no kinetic. Is there any potential? Yes, there is, because potential energy is height energy. But instead of putting our zero of height down here at the ground, we notice that the height isn't changing in the problem. So let's just call that height 0 up here. So we're going to call this the 0 of height. When we do that, that means that there's no potential energy at the beginning either. So relative to this reference level right here, if the ball's not moving and it has no height, that's an initial mechanical energy of 0. Now, you're doing some work because you throw it. You're using some chemical energy to make it move. At the end, well, it's still at the 0 of height. It's still at the reference level, so it's got no potential energy, but it's moving. Therefore, it's got kinetic energy at the end. So our work energy statement in this case tells us the work that was done in the throw equals the kinetic energy of the ball at the end. Here's another problem. Brakes do work slowing down a car. So energy at the beginning, well, that's clearly kinetic. Kinetic energy at the beginning. Then we do some work, and at the end, there's been a change in the mechanical energy because the object has slowed down. It still has kinetic energy, but it's got less than it had before. So we've got kinetic energy at the beginning. We do some work, the brakes do some work, and you end up with a smaller kinetic energy at the end. Now the brakes work should be negative, which is consistent with this being a large amount of Ke and the kinetic energy at the end being relatively small. Now, the work done by the brakes is, of course, related to the thermal energy that's created. Let's write another work energy equation here. A cyclist does work moving up a hill. Okay, so let's put our 0 down here of height, and we'll say energy at the beginning plus work equals energy at the end. Energy at the beginning, there's no height and there's no motion. So it's 0. Energy at the end, well, it's got height, so it's got potential energy, and it's moving, so it's got kinetic energy. So in this case, the work that was done by the bike rider is equal to the potential and kinetic energy of the rider when he reaches this height here. Okay, so that says 0 plus work equals potential plus kinetic. Next, an elevator does work lifting passengers. Well, we'll put our 0 of height down, and this is sort of typical. You put your 0 of height at the lowest point in the problem. So at the beginning, there is no height energy, and they're at rest, so there's no motion energy either. No mechanical energy at the beginning. At the end, there is clearly, as a result of the work done by the elevator motor, at the end, although it's at rest, it does have height, so there's potential energy at the end. So the work done by the motor will be equivalent to the height potential energy at the end. Here's a parachutist descending. So here they are, they open their chute, and then they slow down a bit, but they continue to fall. So there's our 0 of height at the bottom. That means that at the beginning, they did have some height energy. And because they were moving, obviously, they have some kinetic energy too. So that's the initial mechanical energy. Now, work is done by the parachute, work done by the chute. That's what that's supposed to say. Work done by the chute. And at the end, well, they're still moving. They've got some kinetic energy. But relative to our choice of h equals 0, they do not have any potential energy. Now, clearly, the mechanical energy of the system at the end is less because they're moving relatively slowly. That means that, again, that this work done by the parachute, just like the friction work we considered earlier, is negative, representing a loss of mechanical energy for the system. So, writing work energy equations just involves looking at the picture and saying, all right, does it have height, does it have speed at the beginning and at the end? Let's do now an example where we actually solve all the way to the end. So here we've got a cannonball. It's launched by a cannon. Sometime later, it's got height and it's got speed. We're asked to write a work energy equation and then find the work done on the ball during the launch. So we're going to write the work energy theorem here. Mechanical energy at the beginning plus work done in the explosion equals mechanical energy at the end. Now it makes sense to make this our 0 of height at ground level. So that's h equals 0. Right here at ground level, h equals 0, and that means that at the beginning the ball does not have any height, it does not have any motion. Now, work is done by the chemical and reaction, so there's an explosion that takes place, and later that ball flies out, and then later as we visualize it here, we could see that it's moving, so it's got kinetic energy, and at the same time, it's got height, potential energy. let's work over here on the ink pad just because we can do it a little bit more neatly. So we said that energy at the beginning plus work equals energy at the end. Nothing at the beginning. There was work done by the explosion. And at the end, we have kinetic and potential energy for that cannonball. So the work done, then, we can calculate from our kinetic energy formula, 1/2 mv squared, and our potential energy formula, mgh. All of these values are given in the problem. The mass is given as 5 kilograms. The speed over here is 10 meters per second. And the height over here is 8 meters. So we can compute the amount of work that was done on the object. And it works out to be 642 joules. Now, you may wonder, finishing that up, we've clearly finished the example, you may wonder why we calculated the work in this way. Why didn't we use the definition of work, which is a product of force and displacement? The problem with that is that we don't know what the force is from these expanding gases in the chemical explosion. And the distance is basically the length of the cannonball's bore. We don't know what that is either. So it's true in this case, but both F and D are unknowns. And as a result, it's true but not useful. Okay, so there's our solution of this example. And let's consider a final example here. So in this case, it wasn't possible to calculate the work using the product of force and displacement, but in some cases it is. In this final example, it's possible to solve it in two ways. First of all, using the definition of work, force times displacement. And second of all, using a work energy equation. Now we're going to solve it in both ways and show that we get the same thing. All right, so we're going to pull this object up a ramp, okay? Let's first do this by force analysis. So the forces that act on this object as it's pulled up the ramp, well, you've got to be pulling it up the ramp with a tension or a force. Then, of course, there'll be a gravitational force straight down towards the center of the Earth. That's mg. And then there'll be a normal force perpendicular to the ramp. And let's just fix that. Okay, the ramp is frictionless, so there's no friction force. As we've done many times before, we're going to resolve gravity into components. One component perpendicular to the ramp, one component parallel to the ramp. And we know that this angle here has got to be the same as the ramp angle is 8 degrees. So this slide component here, the one down the ramp, is going to be mg sine of 8 degrees. Because the mass is moving at a constant speed, there must be balanced forces. And that tells us that the applied force F has to equal the slide component, which is 250 g sine of 8 degrees. So we can calculate the work then, knowing that this force has got to be the same as this slide component. There's the force, right? Multiplied by the displacement. It's a 20-meter long ramp, so there's the work. Now let's solve the problem. Having solved it by force and getting this answer, we're not going to work it out numerically. We're just going to proceed to solve it now using an energy equation. And we're going to show that we get the same expression. Now, for our work energy equation, we're going to say energy at the beginning plus work equals energy at the end. The energy down here at the beginning, well, it doesn't have any height, but it does have motion, so there's kinetic energy. Some work is done by the pulling force. Up here at the end, well, it's got height, so it's got potential energy. And it's still moving, so it's got kinetic energy. However, because the speed is constant, the kinetic energy here and here is the same, and it will just cancel out. So the amount of work done just equals the potential energy. And we know how to calculate potential energy. It's mgh. So the mass is 250. G is just the G constant. What is the height? Well, it's equal to this height right here. Now that isn't given, but we do know the length of the ramp is 20, and we know this angle down here is 8 degrees, so we can say that the height is, opposite side, will be 20 sine of 8 degrees. Now, if you compare this expression with this expression here, you will see that they are the same. And that is, of course, what we wanted to show. You get exactly the same result solving the problem using force analysis that you did using energy analysis. Same answer both ways. Okay, so that completes our third lesson here. And next time we're going to consider this work energy theorem in a little bit more detail, and we're going to look at mechanical energy conservation.